In this section we're going to discuss part 2 of the projection to volumetric data. So in part 1 we saw a more advanced version of the Fourier slice theorem and filtered back projection. And as I said previously, when you're reading through sections of textbooks that discuss these, you now have a better understanding of how the equations that are shown relate to the simple flow diagrams that we've previously discussed. Now we know that the analytic forms which have been the workhorse previously in CT have been superseded by iterative reconstructors. Now iterative reconstruction has two main categories. We can either talk about algebraic iterative reconstruction or statistical iterative reconstruction. So algebraic iterative reconstruction treats the process as solving a load of linear equations and converging on a solution. The statistical techniques are more advanced and they build in models for the noise and the detection system, the source, and so on and so forth, in order to improve the image. So there is one issue though with, there's two main issues with iterative reconstructors. The first is the time it takes to do the reconstruction, and the second is that the algorithms are what's called non-linear. So that is, if I tweak one of the parameters at this end, at the input end, I don't get a linear response with image quality at the output. And that makes them somewhat difficult to optimize, unlike for filtered back projection, where I can just collect more projection data and I get a linear improvement with my reconstructed image. So we're going to discuss three key spaces here. We have an object space, a detector space, and an image space. Now the detector space is also called the sinogram space. So let's start with the object space. The object space is the space in which the person is represented. So it's typically a person that's being scanned. And if you picture me in a scanner, my body is not split into discrete little voxels, nice neat little cubes that relate to what I'm reconstructing. My body is continuous as the X-rays go from one organ into the next, and so on and so forth. So that object space we interrogate with X-rays and then store them in the sinogram, which is what's called the detector space. So all of those measurements are collected in cylindrical geometry. It might be with a fan beam and helical scanning and so on and so forth, but all that information is coded in D effectively. Then we have our image space. Now the image space is the thing that we're going to reconstruct into, and that's a pixelated representation of O. So that's the relationship there. And we can go backwards and forwards between D and I by back projecting and reprojecting our data. So the equation that sums this up is D equals AO. So D you can think of as a big long vector of our measurements, which is basically our sinogram. A is a matrix which describes the properties of our detector system, and O is the vector of pixels in the image effectively that describe the person in the scanner. Now we know from filtered back projection that the projection is not just the inverse of the back projection. So if we take our projection data and we back project it, we end up with something that's blurry and noisy and is not a really great representation of what the human body should look like. So what we want to do is better than that, and the way we do better than that is by this thing called iterative reconstruction. So the unknown, we've met everything else here. The unknown that we haven't met before is this thing called A, which is this big probability matrix which represents the probability that the X-rays travelling along one of the ray paths contribute to the pixels in the resulting image. So that matrix basically can incorporate all of the scanner parameters that relate our detected data to our reconstructed image. So what we want to do is get O, clearly. We've got D, we want to get O. We want to get a reconstruction of the object. So mathematically, all you would do is, in an ideal case, is rearrange that equation, take the inverse of the matrix A, and that would give you, apply that to your detected data, and that would give you O. Now, unfortunately, we can't do that, and we can't do that for two reasons. The first is that this system of equations, or the matrix that we need to invert, is just too large. It's too difficult to invert. And the other reason is that we can only calculate an approximate system matrix. We don't know all of the parameters exactly that give us A. So we can't just invert A. So what we have to do then is put this in an iterative solver and try and converge on O. Now, there are two ways we can do that. We can do it the algebraic way or the statistical way. Both ways use the same basic recipe. This recipe has 5 steps. So the first thing we do is make an initial estimate of the image, and we can do that just by effectively doing a back projection of our original data. So we've collected our data, we've back projected it, and therefore we end up with an estimate of the image. The next thing we're going to do is project through. Now we've got this image, we can project through it and to get a new set of estimated projection data. So we've got the projection data that we collected, but now what we're going to do is try and estimate a new projection data set. Once we've got that new projection data set, we can then compare the estimated projections to the measured projections, work out how different they are, and whether we want to stop or continue going round and round this iterative loop. So if we do want to continue, we then go on to step 5, which means we apply a correction to make a new estimate, and then we go back to step 2. And effectively we can just go round and round this loop. So in order to give you an idea, we're just going to go through some of these basic components and look at what they look like pictorially. So the first thing we have is an object space, and I've defined this object on a 32 by 32 grid, which gives me 1024 pixels in my image. We then have our sinogram space, which is our collected data. So the sinogram space can either be the sinogram from the data we've actually collected or the new simulated sinogram. And then we have our image space. So we take our sinogram data, we do some form of back projection, and then we end up with our image. And we can go backwards and forwards between our projection space and our back projection space, our sinogram space and our image space, by applying these mathematical operations. So all those parts you've seen before, the part we haven't seen previously is the system matrix. And this is what a system matrix looks like. So you can see we have all of our possible measurements on one axis and all of the possible pixels in the image. So we've got the 1024 possible pixels in the image on the y-axis and all of the possible measurements that we can make on the x-axis. So as I rotate round 360 degrees, all of the line integrals at each of those angles are all unfolded onto the x-axis. And each of those little boxes on that 2D plot there, the number or the colour in it represents the strength of a probability linking those two things. So how strongly a given ray path is linked to a given pixel in the image. And you can see in this particular toy system there were 7,200 possible measurements. So I've only actually used 180 degrees here because I had used a parallel beam geometry rather than a fan beam geometry. The data at 180 degrees looks the same as the data at 0 degrees, so I only needed to go to 180 degrees. If I'd used a fan beam geometry to simulate this data, I would have needed twice as many measurements on the y-axis, because I'd have needed to go to 360 degrees. Right, so we've seen what the system is that we want to solve, so D equals AO, so our detected data is related to our object space just by a matrix of probabilities. We've seen what we want to do, which is just rearrange that equation. We've said we can't do that, so what's the next best thing we can do? The next best thing we can do is go round and round this loop and compare our original data to our system matrix operating on our object, our AO, which is effectively just our simulated projection data. And we can take the difference between those two, and we know that we're going to get the right answer when that difference between those two is minimal. When the difference between the two is minimal, the numbers that we've put in O are a true representation of what the patient was inside the scanner. So this is the iterative algebraic way of doing the reconstruction process. And we can see that all it's effectively doing is solving all of these linear equations that we can see at the bottom of the screen. So the next question is, how do we get the numbers that go in the system matrix? And when we do this algebraically, the numbers that go in the system matrix are simply just the intersections of each of the ray paths with the pixel in the image. So imagine that there is no image in the image on the left hand side there. The ray path that's shown, which is the diagonal black line, crosses each of the squares in the image, and the length of intersection of that line is just a number, and that number then goes into the system matrix there at the desired square. So that probability links a given pixel to an image, a given line integral. Now the actual algebraic recipe, we saw previously the steps of the general iterative recipe, but the specific algebraic recipe looks like this. So we do a forward projection using the system matrix. We calculate the difference of the original forward projection and our simulated forward projection, which we've just done. We weight the difference, so we're going to trust the rays that only go through a few pixels. Then we back project the weighted difference. We divide the back projection by the length just to do of all rays to do a normalization. And then we add the new back projection to the old, and we start again. And this is the loop that we go around in order to do an algebraic reconstruction. Now, the fully statistical iterative reconstruction is a bit more complicated than this. So our system model now looks more sophisticated. Instead of just D equals A plus O, we also have a noise term in there, which is N. And so we have to account for this noise term. And the simple minimization just between our original projection data D and our simulated projection data now looks much more complicated. But although the mathematics itself is more complicated, it allows us to do much more sophisticated improvements on the image. So clearly it takes a lot longer. So in terms of the key steps, we're going to simulate the projection data using a discrete form of the Beer-Lambert law and the system matrix. We're going to back project now the simulated data. We also back project the original projection data. We calculate the ratio of the two back projections and multiply the previous image by this ratio and start again. So that's effectively the correction step there. So you can say we've got effectively the same steps, but they're organized in a slightly different way in order to solve statistically rather than algebraically. Now, why do we do this? We do this because it allows us to do all of these improvements. So we can reduce the artifacts by correctly accounting for the X-ray spectrum. We can improve the spatial resolution by correctly accounting for the detector resolution and the focal spot. This is all modeling I'm talking about. We can improve the contrast in the image by including the spectral response of the detector in our model, and we can also improve the statistics, which gives us reduced dose. So by accounting for all of these, we can significantly improve the image over just doing an iterative algebraic reconstruction. Now, in order to do that, we need these 5 things. We need an object model, a system model, a statistical model, we need a cost function, and we need an iterative algorithm. So that might be MLEM or MAP. There's various different ones that you can use. And each of the different iterative algorithms then has a slightly different form of this equation here at the bottom of the slide. Right. So effectively, we've said we can have a sinogram domain and an image domain, and we can go backwards and forwards between the two. Now, what we've just discussed previously is what's called fully statistical iterative reconstruction. The commercial vendors, in order to work towards this, have introduced lots of steps along the way, and lots of these steps so far aren't what is truly fully statistical iterative reconstruction, and the reason is because it takes so long. So if you've just acquired your CT scan and you want to reconstruct, you want to get the patient off the bed as soon as possible, you don't want to be waiting an hour and a half for your reconstructions to come through because you can't move on to the next patient. So some of the manufacturers have taken what could be classified as shortcut versions of the iterative reconstruction algorithm in order to speed up this process. So early attempts just did things in the image space, so you can think of just a digital camera like the one on your phone. You take a picture. Now, if you've ever seen what the raw image from a CCD looks like, it's nothing like the image that you see on your phone. Right? The raw image looks horrendous. It undergoes a lot of processing in the image space before what's presented to you on your phone. And so that can be an iterative process, but it's not fully statistical iterative reconstruction. It's just iteratively converging on a better form of the image by applying some filters to the image. Now, alternatively, later steps have also had iterative loops in the sinogram space. So you've iteratively improved what the sinogram looks like, iteratively improved what the image looks like, and some steps have now merged the two of those. But that's still not fully statistical iterative reconstruction. To do the full form of the reconstruction, you have to go backwards and forwards from sinogram space to image space each time you go round the loop, and that's what is the bottleneck, and that's the slow process. So trying to unpick exactly what each of the vendors is doing in their reconstruction is difficult, because obviously a lot of this is commercial in confidence, and whilst some schematic representations are published, exact workings of the guts of these reconstructors aren't generally published, and so therefore we have to speculate a bit to what each of the processes is doing under the hood. So hopefully that's now given you a basic overview of what iterative reconstruction is, how it works, the different approaches, and what you need to understand in terms of what you're looking at with regards to what the vendors are telling you.